So TTAs is a groundbreaking robotics project where we are taking AI from virtual worlds and now we're building this technology into the real world and having it interact, compete, collaborate with real humans in a table tennis domain. We wanted to prove that AI doesn't just exist in virtual spaces. It's not just text, right, that you interact with, but you can actually have a physical experience, and the technology is ready for that. Why we set out to do this project is because speed in robotics that is not predetermined is one of the last frontiers in robotics. So typically, if people show videos of robots that are acting autonomously, the videos are sped up because robots are still slow. It's difficult for them to interact with the environment, let alone with people, at the speed that we are accustomed to or that professional athletes are used to. And so this project, I think, transcends that boundary.
A big part of the innovation was reinforcement learning technology that was also the kind of technology that we used in our previous project in GT Sophie, creating an AI agent that's able to beat the best race car drivers in a simulator in Gran Turismo. And it was the first time that an AI system was able to outperform human champions in a real-time control task. There's a huge difference between making an AI system work in a simulator versus making it work in the real world. The goal of this project is to create a robot that can play a sport at expert level in the real world. As soon as you put people into the environment, a robot has to be incredibly robust and responsive to dynamic situations. In table tennis, this is happening at an enormously fast time scale. This is a really important aspect of this challenge, the unpredictability that the human in the environment brings. The time between when the person hits the ball and the robot's able to sense it and plan its action for a shot that it's never seen before is exceedingly small.
The beginnings of the projects were really humble. There was nobody, there was no office. In fact, it was one of the first projects that we started with Sony AI in 2020. And the first person that I recruited for this project was actually Peter Dürr, because I thought he's a person that's going to really make that project successful.
So at Sony, we were really in a unique position to address this problem, because on the one hand, we have decades of robotics experience. And then on the other hand, we are one of the world's best image sensor companies. So we had, from the start, an advantage. We started by putting together a kind of minimum viable system that could react to the ball by bouncing it up and down on the racket. And that very quickly enabled us to build a robot that could also return balls and play long rallies. So that was a relatively quick process to catch up to the state of the art at the time. At some point, we felt confident that we could beat people in the office. We made little progress, little by little. Quickly became clear that some people in the office actually stood out. One of the team members had a background in table tennis. He played competitively. And so the next challenge became beat Naoya. That took us really, really long to accomplish.
So for this project to come to the stage where we are today, there's a number of key innovations we had to make. And the first one is perception. So it's the only system in the world that can measure spin of an unaltered table tennis ball at this speed.
So the goal of perception team is to locate the ball as quick as possible and as accurate as possible. Immediately after opponent hit the ball, we want to locate the ball in 3D space with minimum latency.
We have 9 cameras distributed on these towers to see the ball, to track it in real time. 3 gaze control systems which are in charge to track the spin of the ball. And we have 4 cameras that are in charge of seeing the player and track the racket. This kind of comprehensive system is the eyes for our robot. Without it, the robot cannot see, and thus it cannot move.
The gaze control system, there's 3 of them around the court, and we focus on the ball, we zoom in on it and track it during rallies. Our concern is to measure the spin of the ball. The spin that professional players exert on the ball is quite high. It goes up to 9,000 RPM. And it's quite important because it changes what the strategy should be, how to intersect the ball, and the type of racket motion that you would exert on the ball.
Number 2 is we build a learning mechanism in AI that is trained in simulation and then transfers to the real world. And we use a lot of techniques, a lot of novel techniques, where the robot plays against itself in order to become better in simulation and then bring it to the real world.
When you want to make a robot play table tennis, you could think, okay, let me start programming and write a number of rules. So if there's a topspin, I need to close the angle of the racket a little bit. There's the backspin, I need to open the angle of the racket a little bit. But we know that doesn't work. It doesn't scale to playing table tennis like humans do. So we resort to learning.
In traditional robotics, in robot manufacturing, a robot is separated from people and doing the same thing over and over again. As soon as you put a person in the environment with the robot, everything becomes unpredictable. There is no way that we could prepare the robot for every possible shot that a person could execute in a table tennis match. And in fact, the person who's playing against a robot is going to change their behavior during the course of a single game as a result of any weakness they see on the part of the robot.
Reinforcement learning is learning from trial and error. You reward the robot for doing good things, such as bringing the racket close to the ball or hitting the ball with the racket. And then, with that reward, you update a model that tells the robot how to act, such as it produces more of these good actions in the future.
We have these simulated environments, we reward it for doing good actions, for producing shots that we deem competitive, and it just starts learning on that problem and just slowly gets better and better, letting it solve as much as it can itself. That led to the best results.
And then finally, the system itself. So we computer optimized some of the components of the robot in order to make it as fast and as agile as necessary.
We took inspiration from a SCARA robot. And this is typically a robot that's more belt-driven and has these long arms which are able to swing very fast, mixed with the normal six-axis robot. What you'll notice is that there's three axes, they're actually all in line. And when they all rotate at the same time, their speeds compound.
But then we have wrist joints in the end, which is basically rotating to be able to create a top or backspin. Try to reduce the weight as much as possible, but we also try to maintain the rigidity. And they are actually quite opposite to each other, because if you want to increase the rigidity, you actually add the material. But we really did a lot of work in putting materials only at the spaces that we really want the material to be at.
A complete autonomous robot needs to do three things. It needs to sense, decide, and act. But also a key challenge of the project is integrating them and putting them together appropriately so that high-speed sensing can feed into the decision-making can choose an action, and the robot can execute that action with precision and speed.
From the beginning, we built in a safety process into the project, where we had regular reviews with safety professionals who helped us guide us through the process. And initially, people were wearing helmets and pads and glasses. And as the robot became, more and more validated, and we had safety certification come through, we were able to remove some of those things. And that was a really important piece of making this project successful. For the first time, at this speed, robots are actually interacting with humans.
So the ambition of this project was to create a robot that can compete with human experts. The only way to evaluate whether it has succeeded is by actually playing against human experts.
Since we chose intentionally this problem so we can compare the performance of the robot to the humans, we didn't want to create a situation where the humans are in any way limited by the environment. This office was chosen because it has a ceiling high enough to give us that 5-meter height that's prescribed by the rules of the International Table Tennis Federation. We also asked licensed referees to help officiate, to ensure that we are really playing on a level playing ground.
Generally, a lot of these things you see, you're working in collaboration with someone, they're trying to help the robot. In our problem, it's not like that at all, really. We play our shot, and then we're kind of at the mercy of what the human does. And we've seen, actually, as the performance improves, these top-level players tend to get more and more adversarial. They're really looking for weaknesses.
few seconds before the start of the final couple of matches.
So now is the time that we will have now the chance to beat pro player with all the rules in place.
She's really strong.
So this is match point, and we are about to write history.
Back in serve.
In sport, I think just as in reinforcement learning, you really learn from surprise. So when you play against someone you expect to win and you win, there's not much learning. When you play against someone you expect to win and you lose, or when you play against someone you expect to lose and you win, I think that's when you learn something.
ドライブを下で帰ってきたり、そんなん全陣で下で帰ってきたっていうのは卓球には存在しない。あれは本当に誰もやらない。世界のトップ選手でも見たことない。でも距離感でやったということは人もできる可能性があるということなので。
When you get to that level of superhuman or human expert competitive level, the autonomous system does something unexpected. There were some particular moments, one that we highlight in the article, where the ball hits the net and changes the course of its trajectory as a result. The robot's already planning how to hit the ball before it gets to the net. So the robot had made a decision and a prediction of where the ball was going to be and had started its movement to hit it. And then the ball hit the net, which changed the ball's trajectory. And we saw the robot adjust quickly enough in real time to sort of change where the racket was going and change its hit. To have that sort of change of decision partway through, that was particularly thrilling and impressive to see.
ではとにかく打球点がロボットは速くって、で、後ろに下がらずにスピードのあるボールに関してはスピードのある倍返しのような強いボール。
At Sony AI, we've always focused on building this technology from two angles. One is we want to push the technology and a technology barrier. We want to overcome what's possible today and provide the next step of the technology. We're doing that together with artists, engineers, researchers, sports people, in order to augment their behavior or their capability rather than replace them. And on top, a lot of the projects